welcome to everyone joining us for this insightful and much anticipated webinar on advanced ceramic 3D printing for cutting edge industry and research, organized by Shree Rapid Technologies in collaboration with 3D Ceram. So I am Sonal Khod, Assistant Marketing Manager from Shree Rapid Technologies. I'm honored to be a moderator for today's session. This webinar is designed to raise awareness and provide in-depth knowledge about the advancements and application of ceramic 3D printing, a technology that is transforming industries. We are privileged to have with us two esteemed panelists, 𝗪𝗫𝗀 Pandey, Manager Applications at Shree Rapid Technologies, of experience in additive manufacturing applications. 𝗪𝗫𝗀 has played a key role in implementing cutting-edge 3D printing solutions across various industries. Also, we have Maxence Bourgeois, ceramic expert at 3D Ceram, with more than 10 years of experience in sales applications of 3D ceramic printing. With Maxence brings valuable insight into how 3D Ceram solutions are shaping the future of advanced ceramics. The agenda for today's session is Introduction to Shree Rapid Technologies, where 𝗪𝗫𝗀 will provide a brief overview of who SRT is driving innovation in additive manufacturing, introduction to 3D Ceram and deep dive into ceramic 3D printing. Here, Maxence will give an introduction about 3D Ceram, its product offering, and discuss the applications of advanced ceramic and across industries. Next, we will go to an interactive session where we will launch an interactive poll to gather your insights and understanding on perspective on ceramic 3D printing. And after that, basically during this session, you can submit your questions at any time during the session via the Q&A tab or the chat box in your tab. It will be displayed on your screen. However, our panelists will address all your questions. So we encourage you to participate in this question and ask questions and make the most of this knowledge sharing webinar. Without a further ado, let's begin the webinar and now invite 𝗪𝗫𝗀 to start with the introduction of Shree Rapid Technologies.
Very good afternoon, all. Thank you being here to attend today's webinar. Shree Rapid Technology as a company, 18 years old company in 3D printing, founded by Nitin Chaudhary and Shashidhar Kumar in 2007. As a company, we tried our best to pushing adoption of additive manufacturing across the country. So where we are today, we have installed more than 650 printers in India. We have 95 employees dedicatedly for 40 employees for application service as well. We have pan-India presence. Bangalore and Delhi, we have regional office. In Mumbai, we have head office. Additionally, we have customer innovation center, metal and plastics. These are the sum of images where you can see all the material, all the machines under one roof. So, Shree Rapid Technology, we are to digital manufacturing solution provider. For that, we deal with reverse engineering. We tie up with GIS scanner, and for the reverse engineering software, we are partnership with 3D System, Materialize, Optum. To making a metal powder, we are partnership with ATU. For 3D printing, we are partnership with 3D Ceram, 3D Systems, BMF, Rise 3D, and Minecraft. For inspection software, we partnership with GIS. Finally, we have dimensions for post-processing techniques. So, as a company, we have all the technology from right desktop to production level, like SLA technology, DLP technology, SLS technology, multi-jet printing, 𝗫𝗏𝗏 based technology, direct metal printing. So, what we're going to talk about today, it's really passionate about in 3D printing. The company name called 3D Ceram from France, Limos. They have very rich experience in technical ceramics, and we have been following them for last 6 years. propagate their technology, and train pushing adoption of additive manufacturing, especially in technical ceramics across the country and industries. So, thank you for our partnership with 3D Ceram. Thanks, Max. Please reach out to us for any queries to validate your technical queries in technical ceramics or any demonstration. Thank you so much.
Thank you, Magesh, for your insightful introduction to Shree Rapid Technology. Now I invite Maxence to introduce 3D Serum and take the webinar forward.
Thank you, Sonal. Thank you, Magesh. Can you see the slide? Is it okay?
No, I'm not able to see your screen.
Okay, let me share again. And now, Sonal, is it okay?
Yes, that's okay.
Perfect. Thank you. So thanks again for the kind introduction. Very good morning to all the attendees of the webinar. So during the next few minutes, I would like to give you a more clear understanding regarding our technology and full end-to-end solution for ceramic 3D printing. First of all, let me explain our history, the history of the company, in order to set the context. First cycle of the company started in 2001, and it was R&D. 3D Ceram is a spin-off of a technical center, and 𝗪𝗏𝗪𝗏𝗵𝗵, our co-CEO, was head of this technical center. We started to print and to sell ceramic parts. It was our first business model. Then Richard Guignon joined the company in 2009, and in 2015, so 9 years ago, we decided to change the business model in order to sell complete line, machines, printers, consumable, and know-how to allow our customers to print parts in their own facility. In 2017, the main shareholder became Sinto. Sinto is a Japanese group with revenue more than $1 billion and more than 5,000 employees all around the world. And it gives stability to 3D Ceram. And since 2017, we develop a range of machine, printer, software that I will explain you. So just to compile, we have more than 22 years of experience in ceramic additive manufacturing. And one of the strengths of 3D Ceram is the fact that we started to print and to sell ceramic parts. It was our first business model a few years ago. Few numbers. So we sold the first machine in December 2015, and we have now more than 140 printing lines all around the world. As Magesh said, our headquarters is based in Limoges, French city well known for ceramic in Europe. And to give you an idea, 3D Ceram represents 60 people globally. As I told you, Sinto is the main shareholder since 2017. Sinto represents approx 5,000 people, more than $1 billion for the turnover, and Sinto is a very profitable company. The main and the historical business of Sinto is not ceramic 3D printing. Sinto is a leader for foundry equipment and surface treatment. But Sinto decided to invest in 3D Ceram because they identified ceramic additive manufacturing as a growing business. So, come back to 3D Ceram and our business model. We are what I'm calling a process provider. Process provider, what does it mean? It means that we can assist our customer for each step of the process. Of course, we develop machines, printers, possible to incorporate in semi-automatic printing line. Software as well, dedicated to ceramic 3D printing, always with the objective to increase productivity and decrease production costs. The material, the consumables, so I will show you some video after. It is a mix of ceramic powder and photosensitive organic content, and what we are calling services, technology transfer, which is very important for us. Technology transfer means training and assistance to allow our user to print a lot of good parts as quickly as possible. Few words about the main process of 3D CAM SLA, stereolithography. The two first steps of the process are common for any additive manufacturing process. First, we have to create the CAD file of the part that we want to print. Then, the user have to generate the printing platform. Generate the printing platform means how many parts on the printing platform, printing orientation, and so on and so forth. Then, the SLA machine, the printer, will print the parts, the ceramic parts, layer by layer to the bottom to the top thanks to the slurry. Keep in mind that for SLA machine, the material is a slurry, so a mix of ceramic powder and photosensitive organic content. A blade, a recoater system, will spread a thin layer of slurry on the printing platform, and the UV laser, based on the top of the machine, will cure the area to print. It is a photosensitive process. After, the printing platform will ghost down of a layer of thickness, the blade will spread another layer of slurry, and so on and so forth, in order to print, to shape all the ceramic parts, layer by layer, to the bottom to the top. After, we have a cleaning, a recycling step, in order to save the uncured slurry, which can be reused for the next printing run. And then, as for any shaping process for technical ceramic parts, we have to do two thermal treatments in two different furnaces. First, thermal treatments debinding, to burn, to remove the organic contents, and then sintering at high temperature in order to densify the ceramic parts. And it is only after thermal treatments, debinding and sintering that we can obtain a functional part who can be used for space, healthcare, semiconductor, and so on. Let me show you a quick video of the process. So, as I told you, SLA, stereolithography process, use a slurry. Slurry is a mix of ceramic powder and photosensitive organic contents. Slurry can be high viscosity, low viscosity. It really depends on the customer need. And this slurry will be printed by the SLA printer. So the blade, the recoater system, exactly what you can see on the screen, will spread thin layer of slurry on the printing platform, and the UV laser, based on the top of the machine, will cure the area to print. After, the printing platform will ghost down of a layer thickness, the blade will spread another layer of slurry, and so on and so forth. When the printing of the part is over, we remove the printing platform to the machine. We save the uncured slurry, the uncured material, which can be reused for the next printing run. So at this stage, after printing and cleaning, we have what we are calling a green part, mix of ceramic powder and photosensitive contents cure. So we have to do thermal treatments, debinding, sintering to obtain a fully dense ceramic part. So SLA is what we are calling a top-down process. Some strengths of the top-down process. With top-down process, we don't have any links, any physical links between the part and the support, or between the part and the printing platform. Maybe some of you already know DLP process. With SLA top-down, we don't have links between the part and the support. Also, top-down allows to have no limitation for the size of the printing platform. And then we can have a range of machines that I will show you later on. On top of that, when we increase the size of the UV laser, we also, when we increase the size of the printing platform, we also increase the number of the UV laser in order to decrease the printing time. And definitively, top-down is the right process for mass production and to reach target for part production, as we can have a big printing platform with automatization of the process. As we're speaking about the machine, let me explain more in details our range of printer. So thanks to SLA and top-down process, we can offer a wide range of machines with the same process and the same slurry to allow quick and easy scale-up for our customers. We have the small one, the C101 Easy, with one UV laser inside, and a printing platform of 100 by 100 by 150 mm. We have the medium size machine, the C1000 Flexmatic, with a printing platform of 320 by 320 by 200 mm. And this machine can have 1, 2, or even 3 UV laser in order to decrease the printing time. And we have the bigger one for the mass production or the printing of big ceramic parts, the C3601 Ultimate, with a printing platform of 600 mm square per 300 mm for the Z-axis and 4 UV laser inside. And thanks to the range of machine and the big printing platform, our users can print big parts or lot of parts. You know about lot of part and mass production, additive manufacturing cannot yet compete with CIM, ceramic injection molding, for instance. But for series of thousands or 10,000s of parts, 3D printing and SLA can compete. For instance, if we have a look on the small alumina nozzle that you can see on this slide, this part is used in production for semiconductor application. The size of the part is roughly 5 cm per 5 cm. We can print 4 parts on the small machine, and the printing time per piece is in 20 minutes per part. If you are printing the same part in the bigger machine, you can print more than 100 parts in the printing platform, and in this case, the printing time per part is approximately 6 minutes per pieces. So one time again, when we increase the size of the printing platform, we also increase the number of UV laser inside in order to decrease the printing time per part. Let me say a few words about the mix, the consumables, so the mixture of ceramic powder and photosensitive organic contents. Our users have 3 options. First option, they can print the standard mixes developed and produced by 𝗲𝗏𝗵𝗵𝗵𝗏. Second option, we have an on-demand offer. On-demand means that we have in our facility a team of chemistry and ceramic engineers in order to develop a new formulation with a powder coming from the customers. So if you have your own ceramic powder, if you want to use 3D printing and SLA, we can develop for you an on-demand slurry. And then last option, very important mainly for laboratory, university and research center, keep in mind that all the machines are open. Open system means that any user, customer can develop by themselves their own formulation and their own printing parameters as well. About the standard mixes developed by 𝗲𝗏𝗵𝗵𝗵, just for your information, we developed more than 15 mixes material possible to print with our SLA printers. Mainly oxide, such as alumina, zirconia, HAP and TCP, hydroxyapatite and tricalcium phosphate for implants, cordierite for space application, and others. And we also developed some slurry for nitride, such as silicon nitride and aluminum nitride, mainly used for defense and space application as well. But as I told you, all of our machines are open. So I want also to share with you some examples of material slurry developed not by 𝗲𝗏𝗵𝗵𝗵, but developed by some of our customers using our machine. I have some customers, for instance, we develop formulation for spinel. Spinel is a transparent ceramic who can be used for luxury or defense application. Alumina with short silicon carbide fibers, SiC, PZT, which is piezo, and ferrite. So as you can see, ceramic is very broad. You have a lot of printable ceramics. We develop internally at 𝗲𝗏𝗵𝗵𝗵 the main printable ceramic, but as the machines are open, if you want to develop your own formulation, you can also develop your own slurry. Let me say a few words just before to show you some application about the smaller SLA machine, the C101 This machine is mainly used by laboratory, university, or also industrial for small series of parts, but mainly this machine is used for the development is really designed for the development of new formulation. We have an option on this machine in order to start a printing run with only 15 milliliter of formulation. So this machine is mainly used by the industry, the research center, people who want to develop their own slurry. Few quick words about the medium-sized machine, the C1000 Flexmatic. This machine was really designed a few years ago with two targets in mind. Increase productivity. It is exactly what you can see on the right side of the slide. For instance, you can see 2000 orthodontic brackets printed on the 320 by 320 printing platform. Printing time for 2000 brackets approx 8 hours. So for a company running 24 hours per day, it's possible to print 6,000 parts per day. So increase productivity and decrease production cost as well. About the decreasing of the production cost, it is exactly what you can see on the left side of the slide. We did not develop only the machines, the printers, but also all the equipment for what's happened after the printing. When the printing is over, the customer removes the printing platform, and we have this device with a tilt in order to automatically save the uncured slurry who can be reused for the next printing run. And as I explained you a few seconds ago, even bigger on the C3601 Ultimate printing platform 600 by 600 by 300 mm for the Z-axis. This machine is mainly used for the printing of big ceramic parts. I will show you some application just after. Here you can see some parts for space application, mirror for space application, or some honeycomb for defense application as well. Just before to speak about some application and study case, I would like to say a few words about a very important development released a few months ago. Since few months, we update our machine with an artificial intelligence-based software. You know, for productivity, our customers are looking for 3 key points with additive manufacturing: reliability, repeatability, and cost efficiency. To do that, we develop a 2-step software. First one, before printing, called SeriaSet. The aim of SeriaSet is to bring the 20 years of experience for ceramic 3D printing in one software in order to give advice to the customer and accelerate the learning curve. So it makes process more reliable as all the settings are managed by artificial intelligence. Then, second step of the software, Serialive, which is an artificial intelligence assisted regulation device. In fact, we had sensor in the machine, and according to the value and data of the sensor, there were some real-time adjustments of the parameters machine. Serialive brings repeatability to the process and cost effectiveness as well, as the sensor can accelerate printing speed if all is going well. So after this introduction about the company, SLA process, and the machine, let me show you some applications who already adopted SLA and technical ceramic 3D printing. First application that I want to show you, space and new space. New space is a big market for ceramic additive manufacturing because they need ceramic parts due to the environment, high temperature, cold temperature, mechanical property, gamma ray, and so on. And they want to use 3D printing to decrease the weight of the part. If we can decrease the weight of a ceramic part, they can save fuel, which is very important for space. First example of big part that you can see on this slide for space application, it is an alumina mirror for satellites. This alumina mirror with semi-closed back design is only feasible with additive manufacturing process. As you can see, the size of the part is quite big, 500 millimeter for the diameter of the part, and 50 millimeter for the height of the part. And we need 7 kg of slurry in order to print such part. To give you an idea, the printing time of such part is less than 1 day. It's 23 hours. Obviously, after debinding and sintering still need to be done, but at least you have a rough idea for the printing time. Some optical mirrors are also printed with cordierite and silicon nitride. And it's really my pleasure today to show you this part, just freshly printed a few days ago on the medium-sized machine with silicon nitride slurry. Obviously, debinding and sintering still need to be done. Now, I want to show you 2 applications already in the space. First one, antennas for nanosatellites. Nanosatellites, so very small satellites, are used for low Earth orbit at approx 400, 600 km to the Earth, mainly for telecommunication. They need ceramic part and they need zirconia due to the permittivity of the zirconia. And why do they need 3D printing and SLA? They need SLA in order to print the complex lattice structure that you can see on the slide, and to be able to print this part with low roughness, thin details, accuracy, and repeatability as well. These customers printing zirconia antenna already obtained the space certification a few months ago, so they already launched in the space tens of parts. It's not anymore a project, it is a reality today to use ceramic printing for parts already in the space. Another application that you can see on the bottom of the slide is a thruster for nanosatellites. Thruster is a device in order to change the trajectory, the position of the satellite in the space. And they need ceramic and they need zirconia or alumina due to the heat insulation and the ion conductivity as well. And same things, they need 3D printing and SLA because the design of the part is very complex. You can only shape it with additive manufacturing process. And same things, these customers already obtained the space certification a few months ago, and they already launched in the space hundreds of parts. So it's a reality today to use ceramic 3D printing and SLA for parts already installed in satellite. Last example for space application, it is a mirror support for telescope. As you can see on the first picture, this part was initially designed for metal printing, but metal properties was not okay for this application. So the customer had to switch with ceramic and alumina. So what we did, we started to redesign the part according to the rules for ceramic 3D printing. You can see a picture of the part after printing and the last one after sintering and the brazing of metal insert. The size of the part is roughly 10 centimeter per 10 centimeter to give you an idea. Second application that I want to share with you today is for semiconductor. About semiconductor, we are not printing the small chips, obviously. But in the machine to produce a semiconductor, there are some big alumina parts. These parts are already made with conventional process since years. And now users want to use 3D printing to produce locally the parts and to decrease the production cost. On this slide, for instance, you can see some example of parts such as a suction plate for silicium wafer, a ceramic gas distribution ring, and a robot effector arm, for instance. All these parts are big alumina parts printed by SLA process and already used in the machine to produce the semiconductor. Another applications who already adopted since years ceramic printing is for biomedical implants. Few examples of implants in this slide. We already printed some skull implants, some ace implant as well, and some bond substitute. Most of the implants are printed with HAP, hydroxyapatite, or TCP, 3-calcium phosphate. So first, let me show you more in details what we did for the skull implants. First, the advantage of 3D printing is obvious, because nobody has the same defects. But as you can see on the slide, on the same parts, we have 3 different functions. We have the dense area in the middle for the mechanical property. We have the porous area on the border of the parts to allow the osteointegration of the implants. And we have some big holes all around the implants in order to allow the surgeon to put resorbable sutures to fix the implants with the skull. So you can see on this video, for instance, how the surgeon, so in this case it is Dr. 𝗪𝗲𝗏, head of the maxillofacial surgery at Limoges Hospital French, how he put resorbable sutures. And Dr. 𝗪𝗲𝗏 explained as well that we have a perfect continuum between bone and implants with SLA process. This is why since few months, few years, we have more and more hospital surgeons who prefer to use ceramic and HAP implants instead of titanium implants or PEEK implants. Let me show you, for instance, this example. So same things. You know, it's not a project, as you can see, to use ceramic printing for implants. We already obtained the clinical certification more than 10 years ago in French, and we printed more than 50 skull implants for real human patients. So before to be able to print any skull implants, we had to do the clinical case. And the main focus on the clinical case was to prove the osteointegration of the implants. And it is exactly what you can see on the CT scan. On the first CT scan, you can see the CT scan 1 month after the surgery. So you can see that we have some gap, let's see, between the implants and the skull. And you can see the same CT scan 1 year, 12 months after. We don't have any gap because the osteointegration of the implant is perfect, which means the real skull think that the implant is bone and it will create physical link. So you have a perfect osteointegration of the implants. You have a total biocompatibility and you don't have any risk of rejection of the implants. This was the conclusion of the clinical case, and this is why, as I explained you a few seconds ago, more and more hospital, surgeon, people prefer ceramic implants instead of metal or PEEK implants. Another application for biomedical implants is for dental application. With SLA and 3D printing, we can mainly print zirconia screw, for instance, or zirconia crowns, as you can see on this slide. This part can also be done with other ceramic process, but with 3D printing, it's possible to decrease the lead time and to decrease the cost as well, production cost. And as you can see on the left side for the screw, thanks to SLA process, we can obtain very accurate parts with a good definition for the threads. So another application that I want to share with you today, who already use SLA stereolithography for mass production, is for hydrogen production. Hydrogen is becoming more and more important for the industry, the cars, the plane, and so on. But how do we make hydrogen? Normally, we make hydrogen by cracking CH4 or with the steam. So using SOEC, solid oxide electrolysis cell, you can create pressurized hydrogen that you can use for the industry. So the question is why 3D printing and SLA is interesting for them. They are printing the cell. The white part is a cell, and the cell is between 2 metal interconnects. And in the complete device, you have a succession of cells and interconnects. The exchange is made on the corrugated surface. The corrugated surface increases the reactivity and the mechanical properties of the part. You can only make this design with SLA, and the material is zirconia with 8% of yttrium, so it is a well-known material. And for this application, we are speaking about a huge needs in terms of parts, hundreds of parts per day. So on the medium-sized machine, we can print, for instance, 6 parts in 8 hours. So, you know, one of the most critical points for the democratization of 3D printing is to be cost-effective. And for this application, even in our bigger machine, it was not possible to reach production cost. For the technical points, no problem, but it was not possible to cut the cost. This is why, in order to decrease the OPEX, we developed a specific machine with 2 goals in mind: increase productivity, more parts, and decrease printing time on the same time, and to cut the cost with automatization and no downtime. So to do that, and I will show you a video just after, we develop a machine with 2 printing platforms inside in order to print approx 20 cells on the same time. Not 1, 2, or even 3, but 6 UV laser inside. 6 UV laser in the same ceramic 3D printer to decrease the printing time. And in order to decrease the downtime, which is the time between 2 printing runs, 2 stations for loading and unloading of the printing platform. I will show you a video after, but when the printing run is over, the 2 printing platforms with printed parts goes out of the machine in a station for cleaning. You have a tilt, and all the uncured slurry will automatically be recycled for the next printing run. So let me show you a video of this new machine just installed a few days ago on the customer site. So this machine is ready made for the automatization of the process. So you just need people in order to start the printing run, and after everything is done automatically. As you can see, the 2 printing platforms will automatically go inside. So you have the slurry. So in this case, as we are printing a zirconia cell, the slurry for zirconia with 8% of yttrium slurry. We have the 2 printing platforms with the 2 recoater system, and total of 3 plus 3, 6 UV laser on the top in order to decrease as much as possible the printing time. After, automatically the printing platform goes out in the unloading system. You have the tilt device in order to save the low viscosity uncured slurry, which will be automatically reused for the next printing run. And on the same time, really on the same time, you have a new clean printing platform that you will see just in a few seconds, who will automatically go inside. So a few months ago, you need people to remove the printing platform and to start a new one. With this machine, we have almost no downtime, so no waste of time between 2 printing runs. So this machine is already installed in a few days in the customer site. So he will start to use the machine. And as you understood, the aim of the machine is really to increase productivity and decrease production cost. Let me show you a last application for SLA printing. It is for luxury and jewelry parts. Just to show you what our customers are already pre-printed. Obviously and unfortunately, we are not printing the diamonds that you can see on the slide, but thanks to SLA 3D printing, it's possible to print zirconia. Zirconia can be white, can be black. You can add enamels on the zirconia to add some glossy and shiny color. And if we are doing post-treatments, you can have the glossy and the shiny aspects. So here you can see some cufflinks, some ring, some watch case, and so on. And obviously, one of the main advantages of 3D printing for luxury application is the freedom of the design. You can shape some new design that you can only shape, print with additive manufacturing and SLA process. And other example of parts, so you have some DNA and so on. So now I would like to say a few words about another machine and other process. During the first minutes, I spoke about SLA, process, machine, application, and so on. Now, I will still speak obviously about ceramic 3D printing, but another machine and another process. Since few years, we launched on the market an extrusion-based machine, the MAT, MIT, multi-additive technology. This machine, mainly for laboratory, university, and research center, is based on extrusion processes and can integrate different technology. The MIT can use FFF head, so a filament goes through a nozzle and you can print parts. Or direct ink writing head, it is a paste extrusion system. Or direct pellet extrusion, the material is not filament, is not a paste, it is a same pellet used for ceramic injection molding, for instance. And on top of that, the machine can use a CNC head to do machining to improve the surface aspect of the parts after printing. So this machine, we can integrate different heads, have a printing platform of 200 per 200 per 200 millimeter, and can print ceramic filaments, metal filaments, or ceramic pellets or metal pellets. Even if ceramic is the main know-how at 3D Ceram, keep in mind that this machine can print both ceramic and metal. So here, for instance, about FFF. So FFF is a well-known process. Probably most of you already use FFF process for plastic printing. For instance, a filament goes through a nozzle. It is exactly the same things with ceramic filaments. If you don't know, keep in mind that it is possible to print ceramic parts with FFF process. For instance, on the video, you can see a zirconia part during the printing process, and on the picture, you can see zirconia, alumina, and the black and the gray parts are SiC, silicon carbide. Another process for the MIT is paste extrusion. So if your material is a paste, most of the time it's a mix of ceramic powder and water, it is possible to use direct ink writing paste in order to print parts. So it's not a filament, it's a paste, and the process is direct ink writing. Another process is for direct pellet extrusion. So the material is not filament, is not a paste, it is pellet. So the same pellet already used for ceramic injection molding process, and it's possible to print parts with direct pellet extrusion head. One of the main advantages of this process, it's a very fast, a very quick process. For instance, in order to print this part with direct pellet extrusion, quite a big part, you can see the size of the part is 110 per 110 per 150 mm. The printing time is 45 minutes. And as I told you a few minutes ago, one of the strengths of this machine is the possibility to combine printing and green machining on the same printer. So if you want to improve the surface aspect of the part, for instance, it's possible to print and to machine on the same time. So you can have two heads on the printer. One head for the printing could be FFF or pellet extrusion, and another head for the machining of the part. It's very useful if you want to improve the surface aspect or to improve the accuracy of the part, for instance. So, a few words to conclude. You know, at 3D-Ceram, so as I explained you, we offer different technology, different solution for ceramic 3D printing. SLA for fully dense parts, mass production peak parts who can be used for space, semiconductor, implants, real application, and the MIT, mainly used by university, laboratory, and so on, and based on extrusion process. About SLA, and it's really the vision of 3D-Ceram, we do believe that automatization is mandatory to cut down the price. Every time we touch a part, it costs money. That's first things. Second point is machine learning, artificial intelligence. As I told you, 3D-Ceram is part of Synto Group, and Synto is quite good in automatization. That's what we need to do. Whatever is your need for machine, technology transfer, or parts, we are here with Shree Rapid Technology to assist you to implement additive manufacturing in your current business. And last but not least, keep in mind that 3D-Ceram is organizing with 𝗙𝗵𝗆 the first ceramic AM summit from June 30 to July 2nd in Berlin, Germany. This event will bring together experts, chercheurs, industry professionals to discuss the latest advancement in ceramic additive manufacturing. Do not hesitate to join this event and submit an abstract. This is open to everyone. Thanks a lot. I will stop to share my screen, and if you have any question, do not hesitate to ask us.
Thank you, Max. Thank you for an excellent and in-depth session on 3D-Ceram. So moving on forward, we'll start with the interactive question sessions. So now it's time for to answer your queries. Let's take our first question. Max, you'll get a few questions in your question and answer box.
Okay, so first question, are you able to print metal in the same way? With the MIT, the extrusion machine, yes. Not with SLA. What we develop for SLA stereolithography is really focused on ceramic printing, but for the extrusion-based machine, could be FFF, filament, or pellet extrusion, it's possible to print also metal on the same printer. So not with SLA, but with extrusion-based process, yes, it's possible to print metals such as stainless steel, titanium, copper, for instance.
Okay, the next question is assigned to you.
Okay. How to check the technical commercial feasibility of parts? How to connect? It's a good question. Maybe Magesh, you can help me to answer. I do believe the best option is to contact Magesh at Shree Rapid Technology, and he will check, or we will check together, the feasibility of your project. Magesh, something to add?
Yeah. Hello. Yeah. Great. So you can share your file or information. We can work out how the part can be worked out for techno commercials.
Thank you, Magesh. Next question is a very good one, more about SLA. What's about the stability of the slurry during printing, especially when the height is more? You're right, it's definitively one of the key points of SLA. As you know, the slurry is a mix of ceramic powder and photosensitive organic contents, so we cannot have any sedimentation of the slurry. So it took years for us, but we developed stable slurry Even if we are printing parts during 5-6 days, we don't have any sedimentation of the slurry. Then, during the storage of the slurry, if a customer have to store slurry for weeks, months, we advise them to rotate the slurry. But during the printing process, even if the printing time is quite long, more than 5-6 days, we don't have any sedimentation of the slurry, thanks to the chemical composition of the organic content. Another question, what about baking? So I think you want to speak about the debinding and sintering. For all the process, SLA, FFF, pellet extrusion, after printing, we have to do debinding and sintering. But you know, it's not due to 3D printing. Globally, for all the shaping process for technical ceramic parts, you have to shape the parts, 3D printing, molding, ceramic injection molding, and so on. And after, you have to debind and to sinter the parts. The aim of the debinding process is only to remove the organic content, and the aim of the sintering process in another furnace at very high temperature is to densify the parts. In the case of hydrogen production, the cell stack, so what I show you, what is the minimum quantity of corrugated sheets required? It's a good question, and it really depends on the customer needs. Let me try to answer. The complete device in order to produce hydrogen is called a stack. It depends on the size of the stack, but in one stack, you can have between 20 and 50 zirconia cells in one stack. So if the customer, for instance, want to produce hundreds, thousands of stack, they may need 20,000, 50,000 zirconia cell per weeks, months. So it really depends of what the customer want to produce in terms of productivity. But just to give you an idea, in one stack, in one device, you can have between 20 and 50 zirconia cells. Mechanical property of the parts. Thanks for the question because it's a really good one. I will start with SLA. About SLA, if we are using the same ceramic powder and the same sintering curve, we don't have any difference in terms of property between SLA and conventional process. 3D printing will not increase or decrease the mechanical property, for instance. SLA and 3D printing is just here to, let's say, to try to decrease production cost, decrease lead time. But 3D printing, if we are comparing the same things, so the same ceramic powder and the same sintering curve, 3D printing will not change the mechanical property, the thermal property, and so on. That's the first point. Then, with extrusion process, due to the process, it's another kind of process. You will have some porosity in the part. For instance, with FFF process, you can have a density maximum of 97-98%. So you will slightly decrease the mechanical property of the part. I would say it's normal for FFF process. We cannot compare SLA and FFF. SLA is the right process if you want to make qualified parts for semiconductor, space, implant, and so on. The MIT with FFF, pellet extrusion, and so on is a wide process if you want to quickly print some prototyping and so on. I would like to know the difference in strength of the material when the component is printed in zirconia versus sintered and machined. If you want, we can, if you share your email address, we can share with you some scientific publication. As I explained a few seconds ago, so one time again, I can share some publication. If we are using the same powder and the same sintering curve, we don't have any difference in terms of mechanical property between 3D printing and the same parts made by other process. So if you want, if you share your email contact, we can share with you some scientific publication. What is the smallest part you can print and what is the surface roughness? Okay, so I will answer for SLA. The roughness of the parts without any post-treatments, so just printing, debinding, sintering, is roughly 0.8 micron. RA roughness 0.8 micron for SLA. Smallest parts that we can print, I will answer with the smaller pixel that we can print, or the smallest wall thickness, 100 micron. Then with the smaller parts, it's not only a matter of printing, it's also a matter of cleaning. I am able to remove the part to the printing platform and so on. But to try to answer to your question, smaller pixel or smaller wall thickness printable, 100 micron.
Okay, so we have got so thank you, Max. So those
Thank
were
you.
the questions we have received and we have shared with you. And so yes, going on forward, we as we conclude this insightful session, I'm sorry. So, as we conclude this insightful session, I would like to extend my heartfelt thanks to Max and 3D Ceram team for sharing this expertise and knowledge. A special thanks to Magesh and Shree Rapid Technologies team for organizing and making this webinar a success. Last but not the least, thank you for all the attendees for your enthusiastic participation and engagement. If you wish to connect with us regarding any related queries to 3D printing, please feel free to reach out to us at marketing@shree.com, or you can also contact us at the given number which is displayed on the screen. We look forward to stay in touch with you, and also we will bring more insightful sessions going on forward. Thank you, everyone. Please do connect with us, all the attendees who have more questions or any queries related to 3D Ceram or SRT. Thank you. Thank you, everyone.
Thank you. Bye.
Bye. Bye, Max.